Hi everyone, my name is Taylor Sparks. I'm the editor-in-chief of Integrating Materials and Manufacturing Innovation, and we have a brand new paper to talk about today. It's all about uncertainty in ICME. The lead author is Digonta and corresponding author is Nellippallil at Florida Institute of Technology, with contributions from workers as well at the University of College Dublin. Now, this paper is part of a topical collection that we have happening right now at IMMI about uncertainty quantification for decision support in ICME. So not surprising that the topic of this paper deals with uncertainty in the ICME process then. In this paper, they are going to do something clever to deal with uncertainty. They're going to combine three things together. First off, they're going to do Gaussian process. Yes, they're going to do Bayesian optimization, but they introduce a new thing, this compromised decision support problem, CDSP construct. The idea behind here is we're going to not just be trying to find an optimal solution based off of mathematical minima. Instead, we're going to try and find robust, satisficing solutions rather than chasing a single solution. We're going to look for whole regions that are robust to uncertainty. Let me illustrate. They start obviously showcasing the overall workflow. You're going to find your specific problem information. You're going to formulate it into a Gaussian process model. But importantly, you're going to have this all-in-one formulation and inverse exploration step for your multidisciplinary problem. So why are they modifying Bayesian optimization? I think this figure here is a good place to start. On the left is your traditional Bayesian optimization. You can see that there's a minima, and after some sampling, the traditional approach is going to sort of heavily explore that region. But what if there's large uncertainty here in your model, right? On the right panel, it's showing you the result of their CDSP modified Bayesian optimization. And you see that instead of just focusing on the optimum, the algorithm is actually actively seeking regions that satisfy this robustness requirement, which they've defined in equation 17 in the paper. Robustness, just put it sort of simply, the types of things they're looking for a solution to be robust is that it should have good average performance, but it should also have low sensitivity to uncertainty and have low risk of failing your requirements. So if this is just a sort of mathematical benchmark on a polynomial benchmark, let's look at real data. Okay, here you see the information flow for an actual process for materials called hot rod rolling, right? It's showing you materials, manufacturing, and product disciplines all together. These are more commonly represented in XDSM charts. The XDSM charts are really just what we talk about in material science as structure, process, property, performance sort of linkages. Here you can see where all these different linkages get shown together, showing you how information flows across the different processes. So things like temperature, deformation, grain size evolution, mechanical properties, they all get linked through a series of subsystem models. And those are all Gaussian process surrogates. And because of that, we're able to capture uncertainty all the way through the chain, right? You can actually, as a designer, quantify how uncertainty introduced early in the process, for example, gets actually propagated all the way through to your final product performance. Okay, so let's take a look at how this modified Bayesian optimization actually modifies their search space for a raw material. There's a couple of figures here, figures 9, 10, 11. Here, this first one, this first figure 9 is showing you how this deviation metric, which is what we want to try and minimize for a robust solution, is actually, getting reduced as we go through different iterations, showing us that the solution is finding better solutions that are more robust. And conversely, what we'd expect to see then in figure 10 here with the EMI, that's our error margin index, is that as we iterate, again, we're seeing that EMI rises and that we stabilize above our target threshold, demonstrating that we've identified solutions that remain reliable even though we have uncertainty. And then finally here in figure 11, it's actually showing us the yield strength and the uncertainty with the error bars, right? And it's essentially showing us that we are able to simultaneously improve performance while also managing this uncertainty through this adaptive sampling technique. It's pretty slick. The overall takeaway for me is that these results demonstrate that this proposed method is actually going to be helpful for optimizing more than just performance. It's going to be identifying entire regions of your solution space that are satisficing and that remain so even when you have uncertainty, which is the point of this paper in this special issue. I hope you take a look at it and you can read all about it on the latest issue of IMMI.